The name of this video is Multiple Series Expansion A. That is, we are going to investigate the multiple series expansion for the vector potential A. As always, since A is a vector whereas V was a scalar, it's going to be a little bit more complicated. However, same equations have same solution. So in fact, we can use pretty much the same approach as for V. So let me show a bulk material, which I sketch in this fashion with a hollow region somewhere here. So this is hollow, so there is vacuum here, so it's like a circuit, but it's a bulk circuit. So it's a bulk circuit in general. It's not a wire, it's a bulk circuit characterized by a region here, capital omega, where we have, instead of a rho, a j, which is function of r prime as always. So if we choose here the origin of all vectors O, eventually at this point here, which is a Q point where the j is defined, this we call it r prime. An observation point, capital P, outside capital omega is identified by this vector r, and as always, this distance is small delta norm, if you want, and this is the angle theta exactly as we've seen for the multiple series expansion for V, either using Taylor series or in the appendix. We also have seen it with the Legendre polynomials, which gives the same result. So this is our bulk, and here we have this J, which goes in this direction. So this is our J, and let's consider this J to be a steady current to begin with, okay? In this problem, let's consider it to be a steady current. You know, the next few videos, we're going to discuss about the multiple series expansion for A. All right, so now that we know all that, how can we write the vector potential A? So we know that the vector potential A, we've seen this already in a couple of times, even in Phys 242. So A at an observation point R, both vectors, is given by mu naught over 4 pi volume integral in the region capital omega where J is defined of J vector at R prime vector divided by the distance, which is actually delta, that's what we define here, times the volume, infinitesimal volume, dr prime quantity cube. Great. So now that we know that, and let's assume as always that we are in the condition such that r prime divided by r is much smaller than 1, which means we are far away. So capital P is far away from the current distribution. So under these conditions, we can do the following mapping. Same equations, same solutions. So same equations, EQS for equations, same solutions. So what is the mapping we are going to do? We already encountered something like this, but component by component for V. It was exactly the same kind of shape. So the series is going to be the same series. And so what we used to call V at an observation point R, we're going to map it into capital A vector at R. Similarly, 1 over 4 pi epsilon naught, we map it as always to mu naught over 4 pi. And finally, we map rho at R prime vector to A vector, to J, the current density, of course, J vector at R prime vector, which is the source, okay, in our case is a current. All right, so now that we know this mapping, same equations have same solutions, we can rewrite our potential, vector potential A at the observation point capital R. We can rewrite it. Let's truncate the series to the first two terms, which is the monopole and dipole. So approximately 1 over 4 pi epsilon naught becomes mu naught over 4 pi, as we know. As always, we can factor out something which we don't integrate, which is 1 over r. This we do not integrate on that. And so we're going to go, let's put a bracket here. So mu naught over 4 pi multiplies 1 over r, volume integral, this is the monopole term on capital omega. Instead of rho, in the mapping, you remember here we have the charge, which is rho dr cube. So now we have 1 over r, instead of rho dr cube, we have 1 over r, j vector at r prime vector, dr prime cube. I'm just following this mapping. So if you look at the first two terms of the Taylor or Legendre series we've seen for the multipole series expansion, that's the first term, the monopole term. And similarly, we have the dipole term, which is going to be already getting rid of the cosine of theta using dot product. So we have r vector divided by r cube, which we don't integrate on, dotted cosine of theta, remember that. The integral, and the integral is a vector in this case, the result of the integral, of the weighted average, so r prime, of instead of rho, now we're weighting j of r prime, the r prime cube, which is the prime cube, which is the dipole moment, exactly as before. All right, so this one will exclude this bracket because we have the mu naught over 4 pi in front of the whole thing. And so this means that A of r can be approximated to the first two terms as an A naught, the monopole term of r, plus an A1 of r, where A naught and A1 are respectively these quantities here. So this one is A naught, and this one gives rise to A1, okay? So we have our monopole term and our dipole term, as always. Now, already intuitively, qualitatively, what do you think is going to happen to the monopole term in the case of the magnetostatic field, the magnetic field B? Interrupt for a second, think about it, meditate for a minute, and then try to respond and come back here. Well, clearly, if you remember the fundamental laws of the magnetic field, we know that a magnetostatic field is such that the divergence of B, and this is true actually also in dynamics, is equal to 0, okay? So this means that nobody was ever able to find, up until now, magnetic monopoles. There is no magnetic charge in an algebraic sense where you have north pole and south pole, and you have more north and south, so that the final result is some north. There is no such a thing, okay? We will come back to this later. So we already know that the monopole term must be 0. This has to be 0, okay? Because nobody found monopole. There is no magnetic charge, okay? No magnetic charge. This is the equivalent of Gauss's theorem for the magnetic field. In the Gauss's theorem, we had rho here, whereas here we have 0, so no magnetic charge. Okay, and you can see the notes. I specify a little bit, a few more words about this concept of magnetic charge, which again we will re-explore when studying magnetic materials. Now, what is interesting, however, here is I would like to prove that my math is consistent with this intuition. Of course, all this math comes from the divergence of B equal to 0, because that's the if and only if condition to be able to write B as the curl of A. So to define the vector potential, so of course it's already embedded in the fact that this is 0. I don't have to prove it. I shouldn't prove it. But I want to see if all my math makes sense and is consistent. So how do we do that? Well, the procedure is the usual. We split this bulk circuit into an infinite set. So we split it into an infinite set. Do it in blue here. As always, the spaghetti approach, right? So instead of having small cubes of charge, I have an infinite set of a filiform, that is ideal, filiform flux tubes, which are my ideal spaghetti, okay? And I'll show you one of them, at least part of one of them. So they have to be a closed circuit, right? So for example, they can be something like this. This can be one of these spaghetti, okay? Of course, I didn't keep the cross-section. The cross-section is the same everywhere. This cross-section area is dA everywhere. Okay, and don't confuse A with this A. This dA actually is really dr prime quantity square, if you want. So don't confuse it with this A. They have nothing to do with each other. Of course, just for sketch reasons, I had to make it smaller here, but it's the same. It's an ideal, so it has to be dA everywhere, okay? It's a filiform flux tube. then I have an infinite set of these spaghetti, and that gives me the full conductor. Okay, so let's examine one of them, which will be characterized by a certain central axis here. So this is my gamma, which goes all around, so it's closed gamma. If I take, for example, along this gamma, a point here, so this is my tangent unit vector t, okay, as always, which happens to be also the normal unit vectors at dA, if you want. We've seen this before many times, also in 242. Okay, with that in mind, what is the next step we want to do here? We are examining only A naught, okay? So the only thing in this video, we're only examining A naught at R. In the next video, we're going to examine A1, which is much more complicated because that's non-zero, okay, generally. This one has to be 0, so I just want to get it out of the way and get rid of it. So for one single of this flux tube, obviously this becomes a dA because it's just for one infinitesimal cube. Okay, so what about this dA? All right, so this dA, we can actually rewrite it as, so let me sketch it a little bit further down here because we need some more space. Okay, so this is my dA. Okay, so dA, how do we write it down? Okay, for one single spaghetto. So this is my dA naught at R, okay? All right, so let's look at the overall integration here. So we are basically integrating JR dr cube, okay? This part here, this integral. All right, so how do we proceed to do that? Well, we have mu naught over 4 pi. We have 1 over r, which doesn't get integrated, because the integral is over r prime. Now, the triple integral, since we are doing only for one dA, the surface part of this, so two of them, are accounted by one dA, okay? And so, since we are doing just for a filiform, the integral over dA clearly is just dA itself, as we've seen already many times in 242. And so we end up having j. Let's take the absolute value of j, so j at r prime, okay, without vector. What is the direction of j? Well, the direction of j is actually t, okay, we will remember that. So we have j times dA, that takes into account for the double integral here. What are we left with? We are left with a single integral, which is on a closed line gamma, which is the axis of the filiform flux tube. Of j, the only thing left over is the vector t, its direction. And of this dr cube, of course, dA is already out, so we are only left with dl, if you want, which is dr prime, whatever you want to call it, okay? So this is dl, one infinitesimal element along this gamma axis, which is a closed circuit, obviously. I need to have a closed circuit in order to establish a steady current. All right, what is JDA? Well, JDA, we know, steady conditions is nothing but the current intensity. So it's dI, because it's for one tube, let's call it dI. So we end up having mu naught over 4 pi times dI divided by R, okay, great, which is this quantity here. What about the integral on a closed loop gamma of TDL? Well, let's look at this in the following way. So let's look at, so this is basically a polygon, okay? It's a polygon with infinitesimal elements dl. Let's look at a simple polygon. For example, I start from this point, then I have this vector here, which is T1, dl1, then another one, and so on and so forth. Eventually, all these vectors, they need to come back to the original point. So I start from this point and end up at this point. If I do the rule of summation of these vectors, consecutive vectors in a closed loop, what is the result of that? Clearly 0. Therefore, the result of this integral is clearly 0. As expected, there is no magnetic monopole term, because clearly there is no magnetic charge. So I just confirm what I thought it should be. Since this is true for each of all these flux tubes, we can generalize it and simply say that the overall term A naught, since for each flux tube is 0, the overall term A naught at observation point R is identically equal to 0. Okay, so this is the result that we get here. So we can get rid of all this first term, as I already said. Okay, this is the result of this video. So in this video, to summarize it, multiple series expansion of the vector potential A, We consider a bulk circuit with a big cross-section where there is a steady current J, this fashion, which varies with R prime, same notation as for V. This is the vector potential, which is very similar to scalar potential. The only difference is that you need to do this mapping. V becomes A, 1 over 4 pi epsilon naught mu naught over 4 pi, and rho becomes J vector. When we are far away, we can Taylor expand it or Legendre polynomial expand it up to second order, let's say, so approximately. By means of the mapping, we get what usually is the charge over R and what usually is the dipole moment divided by R square as well. And so this is nothing but Q over R and P dot R over R cube, if you want. Now, A1, we will consider in the next video in detail. We will need a couple of videos to analyze this A1, which is very complicated. A0 is the monopole term. It should be 0 because there is no magnetic charge. This is embedded in here, so it has to be true. We just verified it is true. The verification is also interesting because, again, it's another example where we use an infinite set of filiform flux tubes, our spaghetti, which is basically the approach used in, when considering currents instead of little cubes, which is what we consider when discussing charges. And that's it.